Today's video I would like to introduce you a very nice problem of Croatian Mathematical Olympiad edition 2000. Here is the following information. We have a is strictly superior than 0. We have x1 through x3 be real numbers such that we have the sum of these numbers equal to 0. Okay, our goal, we are going to prove this sum of the natural log of 1 plus a to the x1 base 2 plus log of 1 plus a to the x2 base 2 plus log of 1 plus a to the x3 the base 2 is superior or equal to 3. Okay, in fact this is very nice problem. In order to solve this one, we are going to get rid of this log to get the normal expression and prove this inequality. Okay, go ahead, pause this video if you would like to give that try to this problem. When you are come back to see the full solution. Okay, now let's get into the solution. So in order to prove this one, I'm going to prove this expression. This is our goal. We are going to prove this one. Okay, I'm going to distribute first product, then I'm going to work on the second product. Okay, so first I'm going to work on this product. Okay, so first term is multiplied by first term is given as number 1. For 1 is multiplied by a to the x2 is given as a to the x2 plus the third term, which is a to the x1 plus the last term of first product, a to the x1 plus a to the x2. So how to get this one? Both terms have the same base, so they have different exponents. So when you multiply a by a is given as same a, so the exponent will have the sum of these two numbers by applying the exponent rule. Okay, so now I finish with the first product. Now let's move on to the second product. Okay, so I'm multiplying this one by this one. So by completing this product, I'm going to multiply this term by this term. Okay, so now 1 is multiplied by 1 is given as 1. 1 is multiplied by e to the x3 is given as e to the x3. Let's move on to the second term of this product. So a to the x2 is multiplied by number 1 is given as a to the x2. So by multiplying this one by this one is given as a to the x2 plus x3. So both terms have the same base, but they have the different exponent. Okay, by applying the exponent rule, by multiplying this one by this one is given as the sum of this exponent. So let's move on to the third term. Okay, so for the third term is given as a to the x1 itself plus this one is multiplied by the last term, which is a to the x1 plus x3. I'm always applying the exponent rule here with the same base, but they have different exponents. So now let's move on to the last term. The last term is given as this one is multiplied by number 1 is given as this number itself, which is a to the x1 plus x2 plus the last term. Both terms they have the same base, but they have different exponent, which is a to the x1 plus x2 plus x3. Okay, now I'm going to replace all the sums of these terms. So for this sum equal to 0 because based on the first condition, so we have the sum of these numbers equal to 0. So since the exponent of this one equal to 0, that's mean the whole thing equal to 1. Okay, so I'm going to take this value of 1 and put it next to the original one, so the total of this 1 plus 1 is given as 2. Then I'm going to replace again this term x2 plus x3 with minus x1, because I'm going to move over x1 to the right hand side of this equation. It become minus 1 equals to this sum. Okay, which is this one. So the same thing with this term. So this term is given as minus x2. So the same thing with the last term is given as minus x3. Now what I'm going to do now, I'm going to take a to the x1 with a to the minus x1 together. Okay, so we'll have a to the x1 plus the inverse of this a to x1, which is this one, which I found is given as a to the minus x1 plus the second term. I will have the same thing with the second term. I'm looking for the a to the x2, e to the x2 plus the inverse of e to the x2, which is a to the minus x2, which is this one. Okay, which I found, plus the last term, which is this one. I'm looking for a to the x3. I have a to the x3 plus the inverse of this one, which is a to the minus x3, which I found here. Okay, now I'm going to move over this term over here. Okay, so I will have e to the x1 plus e to the minus x1 is giving us e to the x1 plus 1 over e to the x1. I'm taking the same terms, and put it on this form. Okay, let's set e to the x1 equals capital X. By replacing this one with capital X is giving us x plus 1 over x. By multiplying side by side, we will have x squared plus number 1 is divided by x. On the other side, I have x minus 1 quantity squared equals x squared minus 2 times x plus number 1, okay, is superior or equal to 0. Now I'm going to move over 2x to the right hand side of this inequality. I get x squared plus number 1 is superior or equal to 2x. Now I'm going to divide both sides by x. I'm going to take off this x from right hand side and put it underneath of this one. Okay, so this one is the same as this one, which is superior equal to 2. Okay, so so that's mean this term which I have here is superior equal to 2. This argument follows similarly to this term and this term. That's mean I already found this term is superior equal to 2. This one is also superior equal to 2. This one is also superior equal to 2. That's mean the whole thing, if I'm going to take this original one, 2 which is 2 plus 2 which is 4 plus 2 which is 6 plus 2 which is 8. So the entire thing is superior equal to 8. Now I have proven this one. Okay, now let's move on to our question. So in order to work on this one and get connected to this expression, we are going simply to apply the logarithm on both sides. Okay, but before applying the log, we are going to make sure every individual term must be strictly superior than 1. Okay, because if one of these terms was strictly inferior than 1, because you would have the log of one of these terms negative. Okay, if it is negative, that makes you a problem. You cannot control the inequality. Okay, so we have to make sure all the terms are strictly superior than 1. Okay, let's take the first term. I have as an initial condition, I have a is strictly superior than 0. This means a plus 1 is strictly superior than 1. So the same thing as a to the x1. Okay, so by applying the log on both sides, I will get a log of this term 1 plus a to the x1 is strictly superior than 0. Okay, which is fine. So that's mean this term and this term and this term are the same. Okay, so all are strictly superior than 1. Okay, now it will be easier for us to apply the log on both sides. Okay, now by applying the log on both sides, I will get a log of 1 plus a to the x1 plus the log of 1 plus a to the x2 plus the log of 1 plus a to the x3. Entire thing is superior equal to a log of 8. A log of 8 the same as log of 2 to the 3. A log of 2 to the 3 is the same as 3 of log of 2. Okay, now I'm going to divide both sides by log of 2. I will get here log of 2. This term is divided by log of 2. The same with this term is divided by log of 2. So this one equivalent to the log of 1 plus a to the x1 base 2. This one is equivalent to the log of 1 plus a to the x2 base 2. For the last one is equivalent to log of 1 plus a to the x3 the base 2. Okay, so the whole thing so the whole thing is superior or equal to 3. Okay, now I have proven this inequality. So I have done with this problem. If you are interested in watching this one, don't forget to support us with your like and subscribe. Thank you for watching. I will see you in next video. Bye.